Hey, hello everyone. Welcome to the tutorial session 2. From the last week's tutorial that Maitri set you up for the first assignment, today we are going to discuss a little bit theoretical parts of the content you have seen throughout the lectures, including the topics privacy 1 and 2. And I think so far you have been around 10 days into the assignment 1 and you have some ideas what it's about. And here today our goal is to basically delve a bit deeper into these topics and also solve questions that likely are going to appear on the exam. So you can also be prepared for the type of the questions that is gonna appear. So before we start, you have solved maybe any of them? Yeah, assignment 1. And before we get started, I want to ask you if you have any questions or feedbacks regarding the assignments. Any opinion? Nothing. Okay. And also the question is that what do you think about the problem of membership inference attack? Do you think it's a viable problem to solve or to approach? Is it interesting or not? Yeah. Yeah, please.
I just had a question. It's interesting, but I had a question regarding the assignment. How high are you expecting us to obtain score? Like how much score is achievable by this membership?
We have no upper threshold, and this threshold defined by yourself, since it's a competition like, so whatever the first team achieves is the highest threshold. But it's an open problem, there's no limit how you can achieve. So if you have very good solution, then good for you, you will be top ranked and maybe write the paper.
It's like 0.06, I guess, and
yes,
it's too low. So
you could consider
how high
that
can someone achieve? Let's say, what's the ideal scenario?
100%.
Average score.
So maybe around 20% would be a good baseline. So here also we will discuss some methods that could be also used in your assignments. You could use those methods to increase your score. So I think I remember from last year's scores around 0.20 or 20% true positive rate at 5% FPR was also scoring teams. Yes.
What circumstances of assignment will be considered pass?
Well, there is no pass and fail for the assignments. Definitely ranking is evaluated. Also, the other factors is also dependent since you will write a report. You will present your method in 2 pages of report, and there you could explain if your method is really interesting and novel, then why not? You will get definitely good score. Not novel, something that you shows that you have investigated different methods, specifically the ones that we are presenting here. Yes. And you can alter those whichever you want to get higher. It's just the point is to investigate different properties. Yes, please.
Are we supposed to have like some observable progress by just simply applying the threshold to the to the features?
Which kind of observable? You mean the scores you submit to the
Yeah.
leaderboard? Well, the point is that this assignment is for 2 weeks, and if we could let you see the scores by as you improve, there is a very high probability that someone might just hack the leaderboard and only improve the score based on the feedbacks they receive from the leaderboard. So that's why we keep it hidden to keep the competitive nature of it.
No. What I mean is the easiest attack is to apply a threshold on the
I thought.
right, or on the losses, right? Are we supposed to see something out of that?
Mm-hmm.
Or do we need to apply more complex
Not maybe
attack?
complex. I think the attacks we introduce in this course are pretty good attacks, even in the whole literature. They are, as we will see today's tutorial, that these are really strong baselines, and the point is to implement them. And also, since there's a problem-dependent hyperparameters that you could tune to basically solve specifically for this model and dataset, you could also think of how you can tune these hyperparameters to get higher score. But overall, in methodological sense, the references we have introduced in the assignment sheets are the most viable baselines that exist in the literature. So the problem of membership inference attack that you have seen already is that you are basically trying to infer whether the model has seen this data point or not. So for the initial sense, it might seem some kind of useless or whatever, that you have made up a problem to just give up solution. But it's far more than that. And the problems you solve here in the membership inference attacks is basically the basis for the measuring the privacy in the models, specifically even in the most recent models in such as large language models or vision language models. So in order to benchmark those models to see how private they are, you want to infer whether you can, basically you can infer existence of this model in training data or not. So this is indeed an interesting problem and specifically useful in the literature. And we will delve deeper to see which methods already exist. So in the course, you saw three methods, and one is the threshold base, shadow model base, and likelihood ratio attack, or acronym as LIRA. If we go deeper, the first question you saw in the sheet, if you have taken a look into that, is that what are the similarities and differences between these methods? So we can start by the first method, the threshold-based attack. So what we do here is that we basically say we have a membership inference feature, whether it is model confidence, loss value, or whatever we think that could give us an insight whether the model has seen data or not. This kind of membership inference features are something that would behave differently whether model has seen the data or not. We expect that if the model has seen the data, it will be highly confident, so it could give us a sense whether the model, this data point, is included in the training set of this model. But specifically with this method, there is a problem I've mentioned, as this score is not calibrated. So do you have any idea what this calibration means? Also, I've written a definition, but I want to know what is your ideas about. Yes?
This means that what threshold should we choose as member, non-member, and how we can choose that?
Exactly. And you could come up with an arbitrary threshold. You say that, okay, higher than this threshold is my non-members or members, or lower than this threshold is my non-members. But there's a problem with this arbitrary choice, and that problem is the false positive rate. And you will also, in this session, we will solve the problem of true positive rate and false positive rate, and we will give definition for those in that problem. But with this arbitrary choice, you're accusing the, let's say, the model owner, say that, okay, you have used my data point, but the problem is that that model owner has not used that data point to train the model. So here is the problem of false accusation. Why is this a problem? Since there is a high probability that there is one data point that shows high confidence just because this data point is simple for model to basically classify or infer with whatever the task it's doing on, not because it has seen this data point during the training. So this is why we usually don't use the arbitrary thresholding the membership inference features due to this problem of calibration. And for a calibration definition, you could also see that whether this model's predicted confidence is basically associated with the membership status of this data point. And in the upcoming methods, we will see how different approaches or different methods approach to solve this calibration problem. So the next two methods both use shadow models, but they use the results of these shadow models in a different way. Whatever we call here is as shadow model-based membership inference attack is basically we train shadow models. What do we mean with shadow model is that we select n models and we train them using the data points sampled from the distribution that we suspect the model has seen those distribution. And in half of the models, we include the data point of interest, and in the other half, we exclude it. So we input the model to these input the data to these shadow models, and we create a binary data set to learn an association between in and out, being in and out in a model's prediction, and also its confidence level. And we train a classifier. This could be a very simple classifier, like logistic regression, to basically learn how different confidence scores are associated with the membership status. Yes, please.
I have a question that how we can choose the target data point here, because maybe there are many target data points that we are going to test them later on the test set. So if we just choose, for example, one target data point and remove it from the data set and also include it, and after that see what's happening, is it going to be generalized on other target data points also?
What do you mean by the target data point? The data point that you want to infer the membership status, right?
Yes, that's right.
Okay. And in the membership inference attack problem, we assume that we have a target model and we have a sample data point that we want to infer the membership status. So in our algorithmic setup, that data point is given.
I see. So it's fixed, and we are going.
Yes, we want to see if this data point was used to train the model or not. That's the problem setup. And the problem with this one is that your shadow model base just learns an association. It's also highly probable to overfit the data you have, and it could also give you false positives. And the third model that we have is the likelihood ratio attack. And we also have the same setup of the shadow models in that case too. We have n shadow models. We include the data point in half of the models and exclude it in the other half. But there's a difference within with the previous one in the way that we want to infer the membership status. And this is also one of the novel works by Carlini. He is one of the founders of this field. And I also read a note from him that he mentioned, okay, I looked at the problem, saw people are just doing classification based. What could we do differently? And the idea was to do a hypothesis testing instead of doing a single classification. And I want to know how many of you have a general idea about what is hypothesis testing. Okay, good. Many of you. Perfect. So the novelty of this work was that they proposed to do a hypothesis testing instead of doing a classification. Before we move on to answer the question, basically what is different is that we calculate. Okay, doesn't show. Okay, the equation you see here is likelihood ratio. So how can we interpret this? We observe the model confidence for a given data point, and we want to calculate how much is it probable to see this kind of confidence, given that this observation is sampled from the in distribution. And the denominator does the same observation sampled from the out models. So you're basically taking the ratio of two likelihoods, the probability of seeing such observation in given the first world to the ratio of the second world. We will also get deeper to understand what exactly this means. Please.
Can we consider in and out to be the case where in case it is part of the data set, in and out case it is not part of the data set, something like that?
Yeah, exactly the same. In the in case, you include the data point in the training set of these shadow models, and the out, you exclude it. So the similarities, all three do membership inference. Pretty simple. And the point is that you have a membership inference feature, you extract it, and what is different is the way you actually want to make inference using that membership inference feature. So in shadow model base, what we call a shadow model base is that you learn a classifier on the binary data, but in Lyra specifically, you use shadow models to basically estimate the underlying probability distribution that governs when the models has seen those data versus the case it hasn't seen. And we do this modeling assuming that the model confidence form a normal distribution, and we could sample from that distribution to basically estimate this world. We will also reach the question regarding the Lyra, and we can discuss more there. Do you have any questions? No? Perfect.
For the first case threshold, we can use any metric to identify or to differentiate between them and numbers like entropy loss.
Definitely. As long as you have a hypothesis that this feature you're using has a different behavior when the model has seen those data versus the case it hasn't. So for example, for large language models, for instance, people use multiple features from entropy, the confidence, log probabilities, or whatever that, even the model's internal weights, the gradients, whatever you think that it will behave differently in both worlds.
How many number of shadow models maybe is optimal for shadow model and also Lyra, and how do they differ? I mean, that, for example, one of them needs more shadow models.
I think in the paper they mentioned 96 shadow models. We will also see a model, see a method, forgot the methods, that it requires only one shadow model. And it's dependent on how much cost you can spend on solving this problem. But the overall hypothesis is that the more shadow models you have, the higher your power of the statistical test.
And that's the same approach for both shadow models and also Lyra.
Yes, both of them are similar.
So the best effect is the one who has high TPR and at the lowest. So which of these algorithms keeps the best?
So basically, if you, I will reach to that question in the next one. I will show the figure to basically is a source from the paper that clearly shows which method has the highest TPR in the given FTR. Yes?
In your attack, what exactly is the output of the attack? How exactly do you basically tell the membership probability, like just duration? And duration can be more than one.
Yes. So we assume that this gives us a ratio of 1. So how do you think we can interpret the ratio of 1 here? So we consider the numerator as probability of observing such confidence score given that from out in distribution over the observing such confidence from the out distribution. And if this gives us a ratio of 1, we can infer that, okay, this observation I have is similar for both in and out models, then probably it's not a it's a non-member.
That's what I'm saying. Basically, if there is a difference, we would basically expect that the upper term is much higher than
yes.
The higher this ratio is, like maybe
right.
as that it's a member, but somehow we still have to briefly interpolate the membership likelihood that we just values of it from this ratio. So that's one of the so we have to submit our basically to the score between 0 and 1 probability of this guy's number. But this thing will be between 1 and basically arbitrary large, so we need some kind of form.
Probability.
Probability.
I mean, how we can basically, this is for basically rejecting the null hypothesis. And you wonder if we have to submit the
basically-
probabilities for each data point, then how we can convert this to a probability.
It's basically depending on, you said basically a threshold, how large this ratio have to be so that we can reject the non-account.
Mhm.
Then
Mhm.
if we reject, then we just return one, otherwise zero.
So basically, you have a probability that this comes from in distribution. Usually they consider the ratio of 1 as a decision threshold. In that case, you could reject a null, but it's not basically 0-1 based classification. So let me check that answer to answer shortly. I don't want to make a mistake here. Yes, do.
So I think the threshold we kind of do validation set approach to identify that threshold, maybe try it for different, consider it as a hyperparameter or something.
For the threshold specifically here, you don't have a LDAP set to basically tune it, since the threshold is clear in the equation itself. Since you, as I said, both a numerator and denominator are equal, means the sample non-member. So the threshold of 1 is a logical theoretical threshold you could use basically to classify or something.
So the first approach, it's going to be validation set approach, so to identify the hyper.
Yes, yes. Any questions? So for this case, we had to, in the first case, choose the threshold of 80% and calculate the TPR, FPR, and accuracy. And for the second case, we had to calculate the true positive rate at 20% false positive rate. And the third question was to answer why we usually consider the true positive rate at a low of FPR instead of aggregated metrics like AUC or accuracy. So if you could see, in the first place, we have a threshold in mind. So with higher, for the confidence higher than 80%, we consider member. And if our models or methods prediction is also matches with the true predictions, then that is called the true positive. And for the second case, when the true status is a member, but our method basically predicts non-member, is false negative. And in the case of the false accusation, which we care the most, is that the status is non-member, but we falsely accuse it to be member. And that is called false positive. And for the other case, is the other way around, and we call it true negative. So in this case, if you count it, we have 3 true positive members in the top 3 rows. And for the other one, false negatives is 2 and false positive 1, and the rest is true negative. So TPR, or true positive rate, is defined as the number of true positive over true positive plus false negatives, which is in our case is 60%. And for the false positive rate, we consider the ratio of false positive to false positive plus true negative, which is 20% in our case. And you could also see the equation of the accuracy. There's something simple from machine learning, but it's worth reviewing what it means to basically what these actually measures mean, to do it in a hands-on problem solving. That should be easy. Any questions? Good. And the other question was about what is the true positive rate at 20% FPR? We already solved that. We had 60% at 20% FPR, but how could we approach this problem if this wasn't the case?
We could maybe calibrate threshold in a way that false positive rate would be 20%.
Yeah, exactly. In the problem, in the last problem, we had a threshold where we selected the true positive and false positive based on that threshold. In this case, we have the false positive, but we have to set the threshold in a way that this false positive matches what the question wants. So this is the other way around that you could also solve this. And this has a very important implication that we usually consider the true positive rate at a low FPR. And what this means is that we want to have the false accusation to be as low as possible, such that we falsely accuse the model owner as low as possible. In that case, we have a high true positive rate, means that we detect the members when they are indeed members of this training set.
What if it was not 20%? How would we approach the question if it was different, not 20% in part A, because it's 40%?
In that case, again, you adjust the threshold to such that you have 40% of your observations to be false positives.
We bring it down to 20, so we exclude them?
It's a given parameter to the problem, and let's say 40% in the case. You just consider 40% of your observations, such that 40% of your observations happens to be false positives.
But we need to bring the threshold to 20, right? We have to change.
Yes,
that.
you have to adjust the threshold.
We start excluding from 40% to make sure that it comes to 20% or something.
So basically, you consider a threshold and you continue adjusting it, such that given that threshold, you have 40% of your data fall into the false positives. Or I may misunderstand it.
For example, in part A, and right now it's 20% already said, but if it was 40%, the false positive. Part B asks for 20%, so how?
It's just a coincidence that this happens. It could have been 1%, but since I have few data points, I didn't want to add hundreds of data points here, that's why. But it doesn't matter how many observations you have or how many. In one case, you are given threshold, and based on that threshold, you calculate true positive rate and false positive rate.
Yeah.
In other cases, it's possible that you have your set limit for a false positive rate, and based on that, you adjust your threshold such that this condition for false positive rate is met. I think it didn't answer your question. Students have this aha moment.
I get how it's what it is, but how do we do it is what I'm trying to understand. Just
For the second.
keep on calculating it till the false positive is 20% something. And then at that point we set the threshold.
Yeah, you set the threshold such that you X% of your observations is false positives. Okay, and I think yes, please.
So there was like a threshold 80%. Was it not about like to drop out other pairs because the got more than 80%? Or what is extension for?
Sorry, could you
The
please?
threshold of 80%. I thought it was defined to drop out all the records except for those four. Counters over the 80%.
And this threshold is basically to for your method to set where you draw the line to differentiate between members and non-members. You include all of the observations, but you should draw this line somewhere to basically differ between the members and non-members. That's what the threshold is used for. Any questions? Okay. I think this should answer your question. Part of your question, actually. This is for Lyra, and also you could take a look at the paper. The blue curve you could see here. I could also give an overview of what this figure is. I think many of you should know what is ROC curve. Yeah. Basically, it's alternating between different true positive rate and false positive rates, given all thresholds that you could consider for your binary classification problem. And what is most interesting for us is the regions in this part. And usually in practice, 1% or 5% false positive rate is considered, and they usually report the true positive rates at those FPRs. And the area under each of these curves is also called AUC, or area of under curve, or ROC curve. And this dashed line is the random guessing. So in this case, Lyra happens to be the best model, the best method that performs a higher TPR in given low FPR regimes. And yes, and that's for Lyra, and also the image source from the Carlin's paper. So why we consider the TPR at low FPRs is because the privacy is the worst case scenario. Maybe many of you are coming from the privacy background, and you do not care how bad your model leaks on average, because if your model even leaks on one data point, that's still considered as a leakage. So that's why we usually consider this kind of metrics, TPR, and at lower FPR rather than average case methods measures like AUC or accuracy. That's the sole reason why we do this. So, question here, I forgot the question. Or yes, please.
Can you help me build the equation? What if the model just says one, wherever? What if the model says this is a number for every case? What would be the TPR over 5% at the
Depends on your data set and also the grant root. So maybe all grantors are all members, then yes, your method that achieves high 100% TPR, but it's also possible that it achieves 0 TPR. So it's totally dependent on what you have for grant root. But usually it shouldn't happen from experimental setup, since when you consider the curves for members and non-members, if you extract, for example, model confidence for a simple classification problem, there's always a region that highly overlaps between two areas. And in that case, your model method is not confident enough to basically infer whether it's 100% member or non-member, since by nature, there's an uncertainty involved here.
Okay. Okay.
Yes.
Difference like this, about the confidence distribution for your favorite content signal for members versus for non-members.
Yes.
The same, so it's trivial threshold for not.
Exactly. If you do, there happen in some cases that you could see clear distinction, but that happens very, very rarely in practice. And in most cases, if you plot this, you could also do this for your assignment, and you will see that there's always high overlap between these two distributions. Okay. So as I mentioned, in classification-based methods or shadow model-based threshold, shadow model-based MIA we had in our lectures, is that you learn a decision boundary between the confidence of members versus non-members, and this has a limitation since you have a discriminative approach to your data. You want to learn a decision boundary between these two, and it's highly probable that maybe your model overfits to those data you have and does not generalize well. But on the other hand, what we have with Lyra is we do a statistical hypothesis testing, and we want to estimate how likely it is, given the observations we have from the shadow models, that point happens to be a member. And this likelihood ratio is basically, as I already mentioned in the previous equation, is the probability of observing such confidence X, given that the point comes from the in-distribution versus the probability of observing such confidence, considering that that observation comes from the out distribution. And also, one important point is regarding the hypothesis testing, specifically with likelihood ratio test, is the Neyman-Pearson lemma. Has anybody heard this lemma before? No. So basically, this lemma tells us that given a threshold for our or level alpha test, and alpha happens to be our type 1 error, in this case, for our hypothesis testing, the likelihood ratio test achieves the highest power among all hypothesis testing problems. And highest power here means the statistical power the probability of rejecting the null when it is indeed false. If I want to give you an overview of what hypothesis testing problem is for those who are not familiar with this concept, is that you want to test an effect, and you usually have two worlds. In the first world, you don't want to believe that your hypothesis is wrong, so you phrase it the other way around. You say that, okay, I accept that my hypothesis in this world is wrong, and you phrase it as the null hypothesis, and you wish to reject it such that the other way, the alternative hypothesis, which you wish to be true, becomes true. So you usually set a level alpha or the false positive error, or type 1 error, sorry, the type 1 error, and you wish to accept in order to reject your null hypothesis. And this hypothesis testing problem ends up with the p-value. This p-value basically means the probability of observing such data or such measures that happens to be extreme given that the null hypothesis is true. So we could phrase it this way: consider that our null hypothesis is true, the effect that we don't want to happen, and our p-value ends up to be very low. So it means that this is really, it's not really likely to happen in this world. That's why with low p-values, which happens to be less than this our level alpha test, we reject the null. We say that this observation is not very likely to happen given that this null hypothesis is true. Then we reject it and we accept the alternative hypothesis. And likelihood ratio tests also are a way of doing this by forming this as a ratio between two likelihoods. And due to Neyman Pearson lemma, the likelihood ratio test is powerful in statistical term, and that's why it usually performs better in practice. Just because both the shadow model base and LIRA use the same shadow models, but the point is how they use these shadow models to make inference. The one uses classification model to basically draw the inference. The other does the likelihood ratio test, and likelihood ratio test happens to be theoretically stronger than just classification-based method. That's why it usually performs better in practice. Any questions? Yes.
So, fully get how this is just some balance and ratio, but still need some alpha or some threshold that tell us when we try to reject the this is
yes, indeed.
Likely some value from 1 to how the likelihood ratio is so high that we can check the null hypothesis of there's no difference.
Again, we reach to the same point that when the probability of observing, so basically we sample or model or estimate the null hypothesis given the shadow models, which is modeled by a normal distribution, parameterized by the observations from these shadow models. And this is actually our null hypothesis. And the p-value we get out of this is considered in the ratio with the alternative. And or the other way around, sorry. And this ratio is basically the ratio between these two p-values, considering that one comes from the alternative world and one comes from the null world. And the higher this ratio, the least probable that this hypothesis is true, the null hypothesis is true. So for question 3, part V is that it asks why we do logit or logit scaling is applied to the model confidence. In the LIRA method, as I said, we model the in and out distribution as a normal distribution. So we have to meet this assumption. And if you see these plots, the model confidence highly peak between 0 or 1, and it is not normally distributed. It falls within a range of 0 to 1, and in order to upscale it to be mapped in the range of -infinity to +infinity, and also empirically become normally distributed. That's why they mentioned that they have applied the logit scaling to the model confidences. As also, this is an empirical observations. So usually they don't test whether it is indeed normally distributed or not. They just make the assumption and use it, and it's not usually tested in the literature that doesn't come from the statistical background. So what are the assumptions for the Lyra? Yeah, please.
The logit scaling should be applied to the shadow.
For all of the logits used, for all of the confidences you observe.
Yeah, but because I mean that the model itself is going to be more private, so they do not like to actually provide more information. So if they just rely on confidence, not logit scaling, that would be better for the model owner.
So the point is that the attack scenario you consider in your study. So it could be whether gray box access or attack vector, or white box or black box. So they assume to have a gray box access, and they publish the model confidences. In that case, you could just apply the logit scaling to that and to your test as it is. But there's also cases that the model provider might only provide the outcome label. Even in that case, also, you could also see the papers cited in the lectures. It is possible to do a label-only membership inference attack. It would be different than this one. And in that case, you have to just basically find a way to associate the label you have observed to this kind of membership inference features. Okay. So as I said, we model the observations we have from the shadow models as a normal distribution. And well, the implicit assumption is that these logit confidences are normally distributed. And they also propose a way, if this assumption fails, what happens? We could use non-parametric density estimation, such as kernel density estimation, and you basically, instead of assuming that these are normally distributed, you just run KDE, and then you have the distribution that models your observations. And it's also not flawless. If you do the same, you usually have less statistical power. It means that in the cases that null hypothesis is indeed incorrect, you fail to reject it, or you fail to find the effect you want to find.
Why is that happening?
Well, good question, and answer is I don't know. But in the case that it's normally distributed and you use a normal distribution, so you have low estimation errors. But in the cases that you use a KDE, there's high probability that your estimation is mostly incorrect or is not as accurate as it could be. Then you get lower TPR. Yes.
Are we saying that it becomes normally distributed after applying logit scaling, or is it normally distributed before the scaling?
We do the logit scaling such that they become or map them into the range of -infinity to +infinity, and we observe that they are normally distributed. They are not normally distributed by nature, and this, I'm sorry, this logit scaling does not make them to become normally distributed. After we do a logit scaling on the model confidences, we observe that usually they become normally distributed empirically.
What is applied the logit scaling?
Yes.
The ratio basically.
You cannot just the ratio and the range of 0 to 1 is not really good place to observe such effects. You map it since the normal distribution ranges from -infinity to +infinity, and you map your confidences from a small region to a vast region. such that you can see their behavior in this, let's say, range.
I think the confidence only or the ratio as well, because ratio.
Confidence.
What about the ratio that we have in here?
In this ratio, you mean?
Yeah.
And this is the, basically, you see your confidence and you calculate the probability that this confidence comes from this normal distribution. And this ratio is the ratio between two probabilities.
The normally distribution.
The ratio itself. The ratio itself is a number.
Both the distributions.
Mhm. Okay. Okay. This was for Lira. Any questions? No. And before we move on to the differential privacy topics, I also want to introduce the method. I also forgot its name. It's ARMIA. And it is proposed to be a stronger baseline compared to Lira. And again, it comes to the point that it has shadow models, as we had for Lira. But the point is that how you use those shadow models and your observations from those shadow models to make your inference. And if you could find some statistically superior way to do your inference, then your method definitely will work better. And this one is also dependent on likelihood ratio test, but it is a bit different than what we had in Lira. Performance-wise, you could see compared to Lira, also similar to previous figure you had. In this case, they suggest that ARMIA performs better in Lira, specifically in the low FPR regimes. And in this case, we do pairwise likelihood ratio test. As you will see, Lira is an average case for ARMIA, since in Lira you compare the distribution, your observation for the data point, assuming that one comes from the in distribution and the other one comes from the out distribution. But in this case, you compare the data points one by one, and you aggregate signal. And as your aggregated signal provides enough evidence to reject a null, in that case, you reject it. And instead of doing one versus all, you do one versus one, and you count the number of times your observed data point or observed confidence differs from a random data point. And then if these observations pass a specific threshold, then you can say that, okay, there is a high probability that this basically data point is a member. So in this case, we do likelihood ratio test and as a pairwise, and the score we consider as a MIA is the probability which is aggregated over all data points from the distribution or underlying distribution data or shadow data set you have this in a practical scenario, such that your likelihood ratio, the pairwise likelihood ratio, passes a threshold gamma. Any questions? Yes, please.
These random, so can it appear multiple times?
Oh, what is the point of happening in multiple times, since you want to do a pairwise test, and if it happens multiple times, then the addition doesn't add a new information, since you are doing the same comparison as you did and same as before. But if you add more diverse random data points, you are gathering more evidence that this point is indeed a member. So, how to calculate this likelihood ratio you see here? The starting point would be the use Bayes rule, and you convert this probability of theta given x as probability of x given theta over probability of x, and the same happens to probability of theta given z. So this probability of x given theta is the actually prediction score or softmax of the outputs you observe from your model. one of the tricky points when you use a Bayes rule is this normalization constant you see in the denominator. This is usually impractical to calculate exactly in practice. You have to find a way to estimate it. And what they do is that they propose this equation, which is sum over theta prime is the shadow models you have, and D is the data set you have. But what they do in their real algorithm is just consider the average of the probability observed from the shadow models. There's a way of estimating this quantity. So we can see this full algorithm. Just there's a lot of content, but I will break it down for you. There's two variants of this method. One is the online and one is the offline version. In the online version, you train multiple in shadow models and out shadow models, both of them. But in offline version, you only have out shadow models, or basically models just trained on the data set that is sampled from the same distribution that your target model has been trained on. And you skip the in shadow model training phase, and it is more biased compared to what you have in the online phase, but it is computationally feasible. So you could also test both of them to see which one performs in your assignment. So the first one, this block, what it does is just train in shadow models. It means that include your target data point in the data sets and train k number of shadow models and estimate the probability of x given this equation and store it. And in the next step, which is for the offline version, you estimate probability of out. Again, you have some bunch of shadow models trained on same data, but this time you don't train any in distribution shadow models, and you just estimate the probability of x using the equation below.
But theta is the output, right?
Sorry?
Theta is the output, right?
Theta here in this equation is the shadow model, theta prime. And theta itself is the target model.
But output of the model is
Probability of probability of x given theta is the probability you observe from the output of the model. And you calculate your ratio, ratio x and ratio z. And you calculate your ratio for that observations. And as you can see here, we iterate over the observations in Z, which is your whole data set. You one by one compare your data point to a random data point that is sampled from there and aggregate information. If that specific ratio is larger than gamma, then you add to your C, which is a counter. And finally, your score or membership score is basically the ratio of C over Z. Yeah, that's it. Any questions?
You can just say the intuition of Armia compared to zero.
Okay, let's consider this way. We have n shadow models. Half of them seen the data, half of them has not seen the data. And we observed the model predictions for those shadow models. And you estimate a normal distribution for one for the in distribution and one for out distribution. And what you do in the last step as your decision point is that you consider the probability ratio for the one that comes from in distribution to the out distribution. So basically you are comparing your single data point to the whole distribution that samples the data, that estimates the data distribution. But in the case of Armia, you are doing this likelihood ratio one by one for each of your non-member data points or random data points. So in this way, you could see lira as an average case of Armia. You do here a pairwise likelihood ratio test since you are comparing your data point to each of these random data points. And as more data points, as more evidence is gathered in this for loop, you will see that, okay, it's highly probable that this points to be member. Okay. Yes.
Can C be a member as well, or it has to be a non-member?
It has to be unknown. Since your test is phrased in a way that you want to compare your data point, which you suspect to be a member, to non-member data points, since you want to calibrate your scores, see that, okay, it gives more evidence. Okay. The next topic is the differential privacy. Here you will see more mathematical stuff, content, and also this is something usual for privacy stuff. They usually come up with the privacy or mathematical or theoretical guarantees to prove that, okay, in this case, I have this given guarantee. And this is also the case for the differential privacy. And in differential privacy, we consider two neighboring data sets. This neighboring data sets is that only vary in one data point. And this variation could be addition, removal, or a difference in the feature or whatever. And this is the only thing you have. And you want to see that your probabilistic model's outcome for these two neighboring data sets should not vary more than a given threshold. And this is governed with this given equation. So the first question you had is a data set. You had like 5 people, and 0, 1 indicate whether they are a smoking person or not. And the query of interest for whoever wants to access to this database is that to count the number of smokers. So let's say the neighboring data set is to add your tutor to this data set, and the outcome of this query to the updated D prime should increase from 2 to 3. So what can we infer from here? Any opinions? So it's highly evident that the person has been added to this database was a smoker. So we have revealed information, private information regarding this person. And for this case, we could measure the sensitivity as measured maximum or f of d, which is the outcome of the previous query to the previous database, minus to the new database. And in this case, the maximum sensitivity that we can consider is 1. So in the problem stated, we were interested in exact differential privacy case with epsilon equal 0.5. And the question has asked us to find the parameter b for this Laplace mechanism such that we could preserve this epsilon equal 0.5 guarantee. So we have equation b, the parameter for the Laplace mechanism is equal to delta f over epsilon, and in this case b equals to 2. And in the next step, the question asks us to prove this. Actually, this equation, the b inferred from this equation, leads to epsilon differential privacy, which is exact case. Yes?
But we have to memorize such a stuff that, for example, this is for E and also for Gaussian.
And for the Gaussian one is a bit complicated, to be honest. You are not expected to memorize anything, but in this case, I think it's simple that your sensitivity over the threshold or guarantee you want to preserve equals to the B in Laplace mechanism.
Yeah, but because also in his slides for this chapter, for differential privacy, there were lots of different formula dots. I wonder whether we should actually remember anything or not, and there are
Maybe-
lots of estimations, formulas and something like that.
The best optimal point would be to learn how to derive these equations. But to answer the question whether they will show up in exam or not, then I will have to ask later or discuss this later. Any questions? Okay. Let's prove this. We consider two scenarios. Probability of observing Z as an outcome of the mechanism M over the probability of observing Z as an outcome of the mechanism M applied to the neighboring data set D prime. This gives us this equation. Simple. How did we achieve this? So we want to have our F, but B, is it visible for everyone? As an outcome of mechanism plus Laplace news. And then you could substitute and bring MD to the left-hand side. And in this case, it will become to 1 over 2b exponential of over. So and you consider the ratio between the two. And you use the triangular inequality to basically convert Z minus FD prime to as a FD minus FD prime. And this should give us an inequality. And then this probability ratio will become less than equal to exponential of this term, exponential of FD minus FD prime over B. And we have defined this term FD minus FD prime as our sensitivity. But as you noted, we have delta F to be maximum of this term. So that's why we consider less than equal to the delta F. And then we could count it as delta F over B if you substitute there. And if you set B equals delta F over E, this will lead us to the exact definition of epsilon differential privacy. I think I just gave you the have to go through these steps. The best optimal way to do this would be to try to recreate these steps on your own. And it's relatively easy. It just uses the triangular inequality and also the definition of sensitivity. And yeah, that by just simple replacement, you will end up with this equation. But I suggest you to go through these steps once on your own. So let's apply differential privacy to machine learning models. Well, in the previous example, we just simply considered the sensitivity as the outcome of our mechanism over a neighboring data set. Why don't we just use this sensitivity to the outcome of these weights and simply add noise and consider the sensitivity over the model weights? Yes. Intractability shouldn't be a problem since you just do an addition and the rest of the inference problem is the same as before. Yes, please.
It doesn't make sense to actually change weights and because maybe change adding noise to the weights, it doesn't lead to what we need as a guarantee for differential privacy. It doesn't have a one-to-one mapping. It's more complex than just.
That could be a point of view. Any other opinions? Yes, please.
For you have a lot of weights, so I'm thinking maybe in terms of optimization, it might take a lot of time, maybe personally.
It's just simple addition of noise. Just I add a epsilon a matrix of noises to the
Billions of
the or billions.
second, the weights they keep on being updated. So I don't know.
Makes sense.
We'll have to update them again and again. And it comes from.
What about the adding it and the last step? So the point is that at which point the privacy leak is likely to occur. In the case that you have observed your data point. What you care about in differential privacy is not an aggregated mechanism, but about the individual or effect of individual data points. So you have to come up with a way that account for effect at each iteration that your model sees your data. So in the case that model has not seen your data, great, no privacy leakage. But in the case that during the optimization process, the data point is introduced to the model's training process, then there is a high probability that the privacy leakage might occur. So the main reason you have to do it another way, you find another algorithm, as you already mentioned, there's no point just adding a noise to the weights of the model, since you care about the effect of a single data point that happens to be affected on the model's weights. So it's not something aggregated, it's about individual data points effect. So another issue might be is that the final weights you get after optimization is highly stochastic process. It means that if you have initiated your model parameter weights in a different, using a different algorithm or at a different point, the point or local minima that you will end up is might be largely different than what you have achieved right now. And it's also related to the hyperparameters you select. And overall, I can summarize in this way that this process is highly stochastic and also high dimensional. So you have to find a way to account for the effect of individual data points throughout the process as the data point is introduced to the model. And this intuition that there is no privacy leakage, if the model has not seen the data point, there is no privacy leakage, actually is used in post-on subsampling that we'll see in later. So the algorithm that has been introduced to basically make the model, machine learning models, differentially private is DPSGD. So you have a training data, and you want to use that training data to basically train your model, and you sample a lot. So what this lot means, we will see later on. Or maybe I can ask you if you have any intuition what lot means. Is that, what's the difference between this mini batch?
That whole thing in the lot, and each lot can have fewer. That's why it's different from.
And also we do sampling in mini batch, right?
The sampling.
Okay.
And it is both on sampling and also with replacement. So we sample something with person sampling, and after that we put it back. And again, there is person sampling with same one of them.
And do you know which sampling process do we use in usual mini batch? No. Any other opinions? Okay. We will get to this point in the next slide. but we can go through the what is the process of the PSGD. And in this case, we compute the pre-example gradients. So for each data point that happens to be inside your lot, you have to individually calculate the gradient. And why is that? Because, as I said, you care about the effect of each data point. And in the next step, you have to clip the gradient for that gradient you have calculated, again, to limit the effect of that data point that affects the final weights. And then you aggregate those gradients and add the noise to the aggregated gradients and update your weights, so same as before. The only difference it has is that, first of all, you have to do a lot instead of mini batch sampling. Second of all, you have to compute the pre-example gradients. What happens in reality in the machine learning softwares you use to basically train your models is that the full gradient vector is never formed. It's highly infeasible computationally and from the memory point of view to form the whole gradient vector. And in that case, if you have to do a pre-example gradient, it's a really high bottleneck here. We have to face it, and we will see how we can solve this problem. And usually in reality, they use gradient vector products to not to form the full gradient matrix, but basically just get the final update out of this without fully forming the gradient matrix. Perfect. Any questions? Okay, what's the difference between a batch and a lot? So in a batch, we sample uniformly, and we usually have a fixed size of B. We say that, okay, I have used batch size of 64, and this batch size of 64 was the same in all of the steps throughout the optimization process. And usually the sampling has been done without the replacement. On the other hand, for a lot, you sample with Poisson subsampling. And what is the difference and how they are different is that each data point can be included in this formed lot independently from other data points with a given probability. Let's say we have probability of 1 over L, and each data point with the probability of 1 over L might be included in this lot or not. So the effect of one data point being included in the lot in the previous step or in the current step has nothing to do with the other data points. And the other point is that the lot size is a random variable. Unlike the batch size that we had fixed throughout the optimization process, lot size is never fixed. So we could come up with an expected value for that. Okay, I have expected value of, let's say, lot size of L. But in one iteration, it might be L minus 1. In the other iteration, it will be L plus 1, but unexpected, it will become the size of L. And yeah, and the whole point of this is about Poisson subsampling is that each sample can be included in the lot independent of the others. Is it clear, everyone? Okay. So we have a property of privacy amplification by Poisson subsampling. And the reason is that at each iteration, when you do the Poisson subsampling, there is a probability that some data points are not included in the optimization process. And we reach to the same point. If the model has not seen the data point, then there is no privacy leakage. And this gives us a theoretical, basically, privacy amplification, such that in a multiple iteration, the effect of this data point becomes diluted, and the final privacy leakage you get out of this point becomes lower. And this effect is called by Poisson subsampling and privacy amplification by Poisson subsampling. And the other question was that, okay, we have to calculate the pre-example gradients, and it is highly infeasible. So what we can do? In the case of, for example, gradient, you basically do your forward process and you fully form the gradient matrix and calculate this. Then you do your clipping and then calculate the batch gradient based on the clipped norms. But the other way, ghost clipping is a method that basically comes up with the solution to prevent this from happening, such that we don't need to fool the form gradient matrix. What it does is that it basically does two-step. For each iteration, it does two back propagations. In the first back propagation, it basically calculates the grad norm without the fully forming the gradient matrix. And how it does is that it basically, if you have seen the back propagation equation, at each local weight, you have one, the local error for that node, and one error coming up from the previous layer, preceding layer, say. And you multiply those matrices together to come up with the gradient for that node. So we could use those two vectors to basically clip the norm, and without having to fully form this gradient matrix, we could come up with the clipped norms, and then we do the second back propagation. And then in this case, we do the normal way. And finally, after these two back propagations, we multiply the clipped norms, clipping factors that happen to be RL in this case, to the gradients that has been captured by the second back propagation, and then we end up with the clipping norms that we wanted to from the first place, without having to fully form the gradient vectors.
We just clip the gradients in the first iteration and then use those in second propagation.
You just, in the first iteration, you just basically calculate the clipped norm ratios for each one.
Those in the second.
Yes, exactly. So that's it for DPSGD. And for the final point is differential privacy by Pate. And for exam specifically, I would suggest that you have in mind that you could write the pseudocode for the algorithms, and it might show up. So please have this mind, just a note. And also, I will share these slides afterwards, so you can have access to it. What this confidence noisy Gaussian max aggregation is named with a full sentence is that you have a data point, threshold, and two noise parameters. First, you check it internally whether these aggregated votes of the teachers pass this threshold. If this threshold is passed, then you can add the second noise and return the argmax. And in the case that it doesn't pass this threshold, then you refrain from answering this query. It's a two-step. In this case, you could add higher noise or low noise, I think. I'm not sure about this one. If this conclusion has a max norm that passes the threshold, then you could answer it. Otherwise, you won't answer it. I think it should be clear. So this one was relatively simple problem. You had a vector of vote counts for each class by the teachers. And for the first step was uniform noise of 4.7. And for the second step, you had the noise vector of this. So you could do this step by step. And in the first place, you can add the first noise and to see if it passes the threshold. Then after adding 4.7, you will see that the maximum one, 46.7, is greater than 4.45. Then you pass this if statement. Then you go to the second step. You add the second noise to the initial votes. And in this case, you return the class that has the the highest votes. And if we consider that it starts from 1 to n, 38.9 is the highest vote, and we could return the class 1 as our result. Yes, please.
In the applications in the slide, actually it was mentioned that for large language models applications, it would be the optimal prompt that is actually is going to be out after this algorithm. And in that case, how we can apply this algorithm on the prompt? Not because they're not being very hard and
First, I didn't fully understand your question. Second, I'm not sure about properly remember that paper. We can discuss this offline. So, any other questions related to this? Overall, any questions except this one? So that thank you very much for your time.
yes, yeah, but